Section 4 of The Advance of Science in the Last Half-Century by T. H. Huxley. The influence of the progress of electrical knowledge and invention upon that of investigation in other fields of science is highly remarkable. The combination of electrical with mechanical contrivances has produced instruments by which not only may extremely small intervals of time be exactly measured, but the varying rapidity of movements which take place in such intervals and appear to the ordinary sense instantaneous is recorded. The duration of the winking of an eye is a proverbial expression for an instantaneous action, but, by the help of the revolving cylinder and the electrical marking apparatus, it is possible to obtain a graphic record of such an action, in which, if it endures a second, that second shall be subdivided into 100 or 1,000 equal parts, and the state of the action at each hundredth or thousandth of a second exhibited. In fact, these instruments may be said to be time microscopes. Such appliances have not only effected a revolution in physiology by the power of analyzing the phenomena of muscular and nervous activity which they have conferred, but they have furnished new methods of measuring the rate of movement of projectiles to the artillerist. Again, the microphone, which renders the minutest movements audible and enables a listener to hear the footfall of a fly, has equipped the sense of hearing with the means of entering almost as deeply into the penetralia of nature as does the sense of sight. That light exerts a remarkable influence in bringing about certain chemical combinations and decompositions was well known 50 years ago, and various more or less successful attempts to produce permanent pictures by the help of that knowledge had already been made. It was not till 1839, however, that practical success was obtained, but the daguerreotypes were both cumbrous and costly, and photography would never have attained its present important development had not the progress of invention substituted paper and glass for the silvered plates then in use. It is not my affair to dwell upon the practical application of the photography of the present day, but it is germane to my purpose to remark that it has furnished a most valuable accessory to the methods of recording motions and lapse of time already in existence. In the hands of the astronomer and the meteorologist, it has yielded means of registering terrestrial, solar, planetary, and stellar phenomena, independent of the sources of error attendant upon ordinary observation. In the hands of the physicist, not only does it record spectroscopic phenomena with unsurpassable ease and precision, but it has revealed the existence of rays having powerful chemical energy, or beyond the visible limits of either end of the spectrum, while, to the naturalist, it furnishes the means by which the forms of many highly complicated objects may be represented, without that possibility of error which is inherent in the work of the draughtsman. In fact, in many cases, the stern impartiality of photography is an objection to its employment. It makes no distinction between the important and the unimportant, and hence photographs of dissections, for example, are rarely so useful as the work of a draughtsman who is at once accurate and intelligent. The determination of the existence of a new planet, Neptune, far beyond the previously known bounds of the solar system, by mathematical deduction from the facts of perturbation, and the immediate confirmation of that determination, in the year 1846, by observers who turned their telescopes into the part of the heavens indicated as its place, constitute a remarkable testimony of nature to the validity of the principles of the astronomy of our time. In addition, so many new asteroids have been added to those which were already known to circulate in the place which theoretically should be occupied by a planet between Mars and Jupiter, that their number now amounts to between 200 and 300. I have already alluded to the extension of our knowledge of the nature of the heavenly bodies by the employment of spectroscopy. It has not only thrown wonderful light upon the physical and chemical constitution of the sun, fixed stars, and nebulae, and comets, but it holds out a prospect of obtaining definite evidence as to the nature of our so-called elementary bodies. The application of the generalizations of thermotics to the problem of the duration of the earth, and of deductions from tidal phenomena to the determination of the length of the day and of the time of the revolution of the moon, in past epochs of the history of the universe, and the demonstration of the competency of the great secular changes, known under the general name of the precession of the equinoxes, to cause corresponding modifications in the climate of the two hemispheres of our globe, have brought astronomy into intimate relation with geology. Geology, in fact, proves that, in the course of the past history of the earth, the climatic conditions of the same region have been widely different, and seeks the explanation of this important truth from the sister sciences. The facts that, in the middle of the Tertiary epoch, evergreen trees abounded within the Arctic Circle, and that, in the long subsequent Quaternary epoch, an Arctic climate with its accompaniment of gigantic glaciers obtained in the northern hemisphere as far south as Switzerland and central France, are as well established as any truths of science. But whether the explanation of these extreme variations in the mean temperature of a great part of the northern hemisphere is to be sought in the concomitant changes in the distribution of land and water surfaces of which geology affords evidence, or in the astronomical conditions, such as those to which I have referred, is a question which must await its answer from the science of the future. Turning now to the great steps in that progress which the biological sciences have made since 1837, we are met, on the threshold of our epoch, with perhaps the greatest of all, namely, the promulgation by Schwann in 1839 of the generalization known as the cell theory, the application and extension of which, by a host of subsequent investigators, has revolutionized morphology, development, and physiology. Thanks to the immense series of labors thus inaugurated, the following fundamental truths have been established. All living bodies contain substances of closely similar physical and chemical composition, which constitute the physical basis of life, known as protoplasm. So far as our present knowledge goes, this takes its origin only from pre-existing protoplasm. All complex living bodies consist, at one period of their existence, of an aggregate of minute portions of such substance, of similar structure, called cells, each cell having its own life independent of the others, though influenced by them. All the morphological characters of animals and plants are the results of the mode of multiplication, growth, and structural metamorphosis of these cells, considered as morphological units. All the physiological activities of animals and plants, assimilation, secretion, excretion, motion, generation, are the expression of the activities of the cells considered as physiological units. Each individual among the higher animals and plants is a synthesis of millions of subordinate individualities. Its individuality, therefore, is that of a civitas in the ancient sense, or that of the Leviathan of Hobbes. There is no absolute line of demarcation between animals and plants. The intimate structure and the modes of change in the cells of the two are fundamentally the same. Moreover, the higher forms are evolved from lower, in the course of their development, by analogous processes of differentiation, coalescence, and reduction in both the vegetable and animal worlds. At the present time, the cell theory, in consequence of recent investigations into the structure and metamorphosis of the nucleus, is undergoing a new development of great significance, which, among other things, foreshadows the possibility of the establishment of a physical theory of heredity on a safer foundation than those which Buffon and Darwin have devised. The popular belief in abiogenesis, or the so-called spontaneous generation of the lower forms of life, which was accepted by all the philosophers of antiquity, held its ground down to the middle of the 17th century. Notwithstanding the frequent citation of the phrase, wrongfully attributed to Harvey, omne vivum ex ovo, that great physiologists believed in spontaneous generation as firmly as Aristotle did. And it was only in the latter part of the 17th century that Redi, by simple and well-devised experiments, demonstrated that, in a great number of cases of supposed spontaneous generation, the animals which made their appearance owed their origin to the ordinary process of reproduction, and thus shook the ancient doctrine to its foundations. In the middle of the 18th century it was revived, in a new form, by Needham and Buffon, but the experiments of Spallanzani enforced the conclusions of Redi, and compelled the advocates of the occurrence of spontaneous generation to seek evidence for their hypothesis only among the parasites and the lowest and minutest organisms. It is just 50 years since Schwann and others proved that, even with respect to them, the supposed evidence of abiogenesis was untrustworthy. During the present epoch, the question whether living matter can be produced in any other way than by the physiological activity of other living matter has been discussed afresh with great vigor, and the problem has been investigated by experimental methods of a precision and refinement unknown to previous investigators. The result is that the evidence in favor of abiogenesis has utterly broken down in every case which has been properly tested. So far as the lowest and minutest organisms are concerned, it has been proved that they never make their appearance if those precautions by which their germs are certainly excluded are taken. And, in regard to parasites, every case which seemed to make for their generation from the substance of the animal or plant which they infest has been proved to have a totally different significance. Whether not living matter may pass, or ever has, under any conditions, passed into living matter, without the agency of pre-existing living matter, necessarily remains an open question. All that can be said is, that it does not undergo this metamorphosis under any known conditions. Those who take a monistic view of the physical world may fairly hold abiogenesis as a pious opinion, supported by analogy and defended by our ignorance. But as matters stand, it is equally justifiable to regard the physical world as a sort of dual monarchy. The kingdoms of living matter and of not living matter are under one system of laws, and there is a perfect freedom of exchange and transit from one to the other. But no claim to biological nationality is valid except birth. In the department of anatomy and development, a host of accurate and patient inquirers, aided by novel methods of preparation, which enable the anatomist to exhaust the details of visible structure and to reproduce them with geometrical precision, have investigated every important group of living animals and plants, no less than the fossil relics of former faunae and florae. An enormous addition has thus been made to our knowledge, especially of the lower forms of life, and it may be said that morphology, however inexhaustible in detail, is complete in its broad features. Classification, which is merely a convenient summary expression of morphological facts, has undergone a corresponding improvement. The breaks which formerly separated our groups from one another, as animals from plants, vertebrates from invertebrates, cryptogams from phanerogams, have either been filled up or shown to have no theoretical significance. The question of the position of man as an animal has given rise to much disputation, with the result of proving that there is no anatomical or developmental character by which he is more widely distinguished from the group of animals most nearly allied to him than they are from one another. In fact, in this particular, the classification of Linnaeus has been proved to be more in accordance with the facts than those of most of his successors. The study of man as a genus and species of the animal world, conducted with reference to no other considerations than those which would be admitted by the investigator of any other form of animal life, has given rise to a special branch of biology known as Anthropology, which has grown with great rapidity. Numerous societies devoted to this portion of science have sprung up, and the energy of its devotees has produced a copious literature. The physical characters of the various races of men have been studied with a minuteness and accuracy heretofore unknown, and demonstrative evidence of the existence of human contemporaries of the extinct animals of the latest geological epoch has been obtained. Physical science has thus been brought into the closest relation with history and with archaeology, and the striking investigations which, during our time, have put beyond doubt the vast antiquity of Babylonian and Egyptian civilization, are in perfect harmony with the conclusions of anthropology as to the antiquity of the human species. Classification is a logical process which consists in putting together those things which are like and keeping asunder those which are unlike, and a morphological classification, of course, takes notes only of morphological likeness and unlikeness. So long, therefore, as our morphological knowledge was almost wholly confined to anatomy, the characters of groups were solely anatomical. But as the phenomena of embryology were explored, the likeness and unlikeness of individual development had to be taken into account, and, at present, the study of ancestral evolution introduces a new element of likeness and unlikeness which is not only eminently deserving of recognition, but must ultimately predominate over all others. A classification which shall represent the process of ancestral evolution is, in fact, the end which the labours of the philosophical taxonomist must keep in view. But it is an end which cannot be attained until the progress of Paleontology has given us far more insight than we yet possess into the historical facts of the case. Much of the speculative phylogeny, which abounds among my present contemporaries, reminds me very forcibly of the speculative morphology, unchecked by a knowledge of development, which was rife in my youth. As hypothesis, suggesting inquiry in this or that direction, it is often extremely useful, but when the product of such speculation is placed on a level with those generalizations of morphological truths which are represented by the definitions of natural groups, it tends to confuse fancy with fact, and to create mere confusion. We are in danger of drifting into a new Naturphilosophie worse than the old, because there is less excuse for it. Boyle did great service to science by his sceptical chemist, and I am inclined to think that, at the present day, a sceptical biologist might exert an equally beneficent influence. Whoso wishes to gain a clear conception of the progress of physiology since 1837 will do well to compare Müller's Physiology, which appeared in 1835, and Drapier's edition of Richard's Nouveaux Éléments de Botanique, published in 1837, with any of the present handbooks of animals and vegetable physiology. Müller's work was a masterpiece, unsurpassed since the time of Haller, and Richard's book enjoyed a great reputation at the time, but their successors transport one into a new world. That which characterizes the new physiology is that it is permeated by, and indeed based upon, conceptions which, though not wholly absent, are but dawning on the minds of the older writers. Modern physiology sets forth as its chief ends, firstly, the ascertainment of the facts and conditions of cell life in general. Secondly, in composite organisms, the analysis of the function of organs into those of the cells of which they are composed. Thirdly, the explication of the processes by which this local cell life is directly or indirectly controlled and brought into relation with the life of the rest of the cells which compose the organism. Fourthly, the investigation of the phenomena of life in general, on the assumption that the physical and chemical processes which take place in the living body are of the same order as those which take place out of it, and that whatever energy is exerted in producing such phenomena is derived from the common stock of energy in the universe. In the fifth place, modern physiology investigates the relation between physical and psychical phenomena, on the assumption that molecular changes in definite portions of nervous matter stand in the relation of necessary antecedents to definite mental states and operations. The work which has been done in each of the directions here indicated is vast, and the accumulation of solid knowledge which has been effected is correspondingly great. For the first time in the history of science, physiologists are now in the position to say that they have arrived at clear and distinct, though by no means complete, conceptions of the manner in which the great functions of assimilation, respiration, secretion, distribution of nutriment, removal of waste products, motion, sensation, and reproduction are performed, while the operation of the nervous system as a regulative apparatus, which influences the origination and the transmission of manifestations of activity, either within itself or in other organs, has been largely elucidated. I have pointed out, in an early part of this chapter, that the history of all branches of science proves that they must attain a considerable stage of development before they yield practical fruits, and this is eminently true of physiology. It is only within the present epoch that physiology and chemistry have reached the point at which they could offer a scientific foundation to agriculture, and it is only within the present epoch that zoology and physiology have yielded any very great aid to pathology and hygiene. But within that time they have already rendered highly important services by the exploration of the phenomena of parasitism. Not only have the history of the animal parasites, such as the tapeworms and the trichina, which infest men and animals with deadly results, been cleared up by means of experimental investigations and efficient modes of prevention deduced from the data so obtained, but the terrible agency of the parasitic fungi and of the infinitesimally minute microbes, which work far greater havoc among plants and animals, has been brought to light. The particulate or germ theory of disease, as it is called, long since suggested, has obtained a firm foundation, in so far as it has been proved to be true in respect of sundry epidemic disorders. Moreover, it has theoretically justified prophylactic measures, such as vaccination, which formerly rested on a merely empirical basis, and it has been extended to other diseases with excellent results. Further, just as the discovery of the cause of scabies proved the absurdity of many of the old prescriptions for the prevention and treatment of that disease, so the discovery of the cause of splenic fever and other such maladies has given a new direction to prophylactic and curative measures against the worst scourges of humanity. Unless the fanaticism of philozoic sentiment overpowers the voice of philanthropy, and the love of dogs and cats supersedes that of one's neighbor, the progress of experimental physiology and pathology will, indubitably, in course of time, place medicine and hygiene upon a rational basis. 2 centuries ago, England was devastated by the plague. Cleanliness and common sense were enough to free us from its ravages. 1 century since, smallpox was almost as great a scourge. Science, though working empirically and almost in the dark, has reduced that evil to relative insignificance. At the present time, science, working in the light of clear knowledge, has attacked splenic fever and has beaten it. It is attacking hydrophobia with no mean promise of success. Sooner or later it will deal, in the same way, with diphtheria, typhoid, and scarlet fever. To one who has seen half a street swept clear of its children, or has lost his own by these horrible pestilences, passing one's offspring through the fire to Moloch seems humanity, compared with the proposal to deprive them of half their chances of health and life because of the discomfort to dogs and cats, rabbits and frogs, which may be involved in the search for means of guarding them. An immense extension has been effected in our knowledge of the distribution of plants and animals, and the elucidation of the causes which have brought about that distribution has been greatly advanced. The establishment of meteorological observations by all civilized nations has furnished a solid foundation to climatology, while a growing sense of the importance of the influence of the struggle for existence affords a wholesome check to the tendency to overrate the influence of climate on distribution. Expeditions, such as that of the Challenger, equipped not for geographical exploration and discovery, but for the purpose of throwing light on problems of physical and biological science, have been sent out by our own and other governments, and have obtained stores of information of the greatest value. For the first time we are in possession of something like precise knowledge of the physical features of the deep seas, and of the living population of the floor of the ocean. The careful and exhaustive study of the phenomena presented by the accumulations of snow and ice in polar and mountainous regions, which has taken place in our time, has not only revealed to the geologist an agent of denudation and transport, which has slowly and quietly produced effects, formerly confidently referred to diluvial catastrophes, but it has suggested new methods of accounting for various puzzling facts of distribution. Paleontology, which treats of the extinct forms of life and their succession and distribution upon our globe, a branch of science which could hardly be said to exist a century ago, has undergone a wonderful development in our epoch. In some groups of animals and plants, the extinct representatives already known are more numerous and important than the living. There can be no doubt that the existing fauna and flora is but the last term of a long series of equally numerous contemporary species, which have succeeded one another by the slow and gradual substitution of species for species in the vast interval of time which has elapsed between the deposition of the earliest fossiliferous strata and the present day. There is no reasonable ground for believing that the oldest remains yet obtained carry us even near the beginnings of life. The impressive warnings of Lyell against hasty speculations based upon negative evidence have been fully justified. Time after time, highly organized types have been discovered in formations of an age in which the existence of such forms of life had been confidently declared to be impossible. The western territories of the United States alone have yielded a world of extinct animal forms, undreamed of 50 years ago. And wherever sufficiently numerous series of the remains of any given group, which has endured for a long space of time, are carefully examined, their morphological relations are never in discordance with the requirements of the doctrine of evolution, and often afford convincing evidence of it. At the same time, it has been shown that certain forms persist with very little change, from the oldest to the newest fossiliferous formations, and thus show that progressive development is a contingent and not a necessary result of the nature of living matter. Geology is, as it were, the biology of our planet as a whole. In so far as it comprises the surface configuration and the inner structure of the earth, it answers to morphology. In so far as it studies changes of condition and their causes, it corresponds with physiology. In so far as it deals with the causes which have affected the progress of the earth from its earliest to its present state, it forms part of the general doctrine of evolution. An interesting contrast between the geology of the present day and that of half a century ago is presented by the complete emancipation of the modern geologist from the controlling and perverting influence of theology, all-powerful at the earlier date. As the geologist of my young days wrote, he had one eye upon fact and the other on Genesis. At present, he wisely keeps both eyes on fact, and ignores the Pentateuchal mythology altogether. The publication of the Principles of Geology brought upon its illustrious author a period of social ostracism. The instruction given to our children is based upon those principles. Whewell had the courage to attack Lyell's fundamental assumption, which surely is a dictate of common sense, that we ought to exhaust known causes before seeking for the explanation of geological phenomena in causes of which we have no experience. But geology has advanced to its present state by working from Lyell's axiom, perhaps I ought rather to say Button's axiom, for that great naturalist and writer embodied the principles of sound geology in a pithy phrase of the Théorie de la Terre, pour juger de ce qui arrive, et même de ce qui arrivera, nous n'avons qu'à examiner ce qui arrive. And to this day, the record of the stratified rocks afford no proof that the intensity or the rapidity of the causes of change has ever varied, between wider limits, than those between which the operations of nature have taken place in the youngest geological epochs. An incalculable benefit has accrued to geological science from the accurate and detailed surveys which have now been executed by skilled geologists employed by the governments of all parts of the civilized world. In geology, the study of large maps is as important as it is said to be in politics, and sections, on a true scale, are even more important, in so far as they are essential to the apprehension of the extraordinary insignificance of geological perturbations in relation to the whole mass of our planet. It should never be forgotten that what we call catastrophes are, in relation to the earth, changes, the equivalents of which would be well represented by the development of a few pimples or the scratch of a pin on a man's head. Vast regions of the earth's surface remain geologically unknown, but the area already fairly explored is many times greater than it was in 1837, and, in many parts of Europe and the United States, the structure of the superficial crust of the earth has been investigated with great minuteness. The parallel between biology and geology which I have drawn is further illustrated by the modern growth of that branch of the science known as petrology, which answers to histology, and has made the microscope as essential an instrument to the geological as to the biological investigator. The evidence of the importance of causes now in operation has been wonderfully enlarged by the study of glacial phenomena, by that of earthquakes and volcanoes, and by that of the efficacy of heat and cold, wind, rain, and rivers as agents of denudation and transport. On the other hand, the exploration of coral reefs and of the deposits now taking place at the bottom of the great oceans has proved that, in animal and plant life, we have agents of reconstruction of a potency hitherto unsuspected. There is no study better fitted than that of geology to impress upon men of general culture that conviction of the unbroken sequence of the order of natural phenomena throughout the duration of the universe, which is the great, and perhaps the most important, effect of the increase of natural knowledge. End of Section 4. End of the advance of science in the last half-century. This has been a Librivox recording. All Librivox recordings are in the public domain.